We will get to practice problem number 2 right now. Let me read it. It says below are numbers of enrolled students in thousands and numbers of burglaries for randomly selected large colleges in a recent year. So just below there, you see the enrollments for 10 large colleges. Keep in mind those are in thousands. And then the number of burglaries that occurred, I assume, on the college campus over the course of a recent year. So we'd like to know, for one, is there a correlation between the size of the college and how many burglaries they might experience over the course of a year? You might say, well, yeah, I really think there's a correlation there between how many students there are and how many burglaries might occur. As enrollment goes up, I would imagine burglaries do too. And I think you're right, but then even more so, what's the strength level between those? Is it strong, moderate, weak, that sort of thing. Okay, so in part A, we are going to use Statcrunch to create a scatter plot of the data. Let me show you how to do that right now. If you don't have your Statcrunch up, I recommend pausing the video and doing that. Okay, so once you have your Statcrunch up and you're looking at the empty spreadsheet, enter the enrollment data as the variable 1 column. So we're going to create 2 columns, one for the enrollment, one for the burglaries. Create your first column for the enrollment data. We're going to think of that like the X variable. And the burglary data, put that under column 2. We'll think of that like the Y variable. Okay. Also, by the way, in Statcrunch, while you're typing those in, you might find it helpful. You can go up to the name of the column where it says var1, var2. You can change those. In this case, I like to change mine to be enrollment, title that first column, and then title the second column burglaries. And then if you're flipping back and forth, you don't forget what those things represent. Now it makes sense here to call enrollment the X variable. If you remember the X variable is the explanatory variable, and Y is the response variable. So we would think the higher the enrollment gets, that causes a response of more burglaries, we think, perhaps. That would be intuitive anyway. Okay, once you have all that data entered in, takes a moment. You're entering 20 points of data, right? We are going to then create the graph. So, see the shadows in the way here. Let me get that off. How do we create the graph? Well, go to graph and then hover down to scatter plot. You'll have to select, I believe you'll have to select your 2 columns. So if you left them var1 and var2, you select those, or if you change the names, select those. Doesn't matter which order you do it in. Select your 2 variables and then hit compute, and you should see a nice plot of all those data points. Really nifty. Okay. Now just looking at the data points, decide if you think it's linear. Now it doesn't mean that all the points have to be on a perfectly straight line, but do they more or less follow a trend? Are they linear? And I'm gonna say yeah. Looking at that scatter plot, this is linear data. I'm actually gonna pull mine up at the same time here, so I'm gonna go to graph, scatter plot. The X variable, okay, is enrollment. Y variables, burglaries, hit compute. Yeah, that's a linear graph, right? So it, as enrollment goes up, so do the burglaries. Now one might argue there's kind of a curve happening there. Maybe, but I can certainly picture a line going right dead center through it and estimating all those points really, really well. Okay, so it says if it's linear, calculate the correlation coefficient. So how do we do that? Well, Statcrunch will do it for us. Okay. So I'll just show you part B here. So go to Stat, then hover over to click Summary Stats and Correlation. And so I'll get rid of my, so Stat, Summary Stats, Correlation. Now we'll have to click on our two variables. You might have to, if you've got a PC, just hold down Control as you click so you can get both of them. If you've got a Mac, I don't know. All right, so click both of those and then hit Compute, and it should give you the correlation there. And so if you round that to 3 decimal places, you should get this number right here, 0.888. So we'd say, wow, okay. Yeah, there's definitely a correlation, a pretty strong one too, 0.888. That's getting up there. We're not asked to interpret or anything, just noticing. And then part C says, does the value of R change if the enrollments are listed as what they really are, 32,000, 31,000, 53,000, and so on. So our enrollments, remember, we just entered them as 32, 31, 53, 28, right? If we change those to actually be thousands, does that change this number? Well, I'll invite you to take a look at it. Go ahead and change all 10 of those enrollment figures to have 3 zeros on the end, and then go and compute this correlation coefficient a second time. Will it change? And the answer is no. In fact, even the scatter plot, when you create a scatter plot in Statcrunch, the scatter plot would look exactly the same. They would just scale that horizontal axis at the bottom to have the thousands now. But the correlation, the scatter plot would look identical, and so the correlation coefficient should be the same. The scaling should not matter, and it doesn't. Okay, let's move on. So you see at the top of page 5, it says some cautions on the correlation coefficient. Let me just read those briefly here together. You might want to read back through them in a bit more detail. But what I'm trying to get across is what are like the limitations of the correlation coefficient. And this is where people start to abuse statistics. So I say numbers don't lie, but poor interpretation is often misleading. So caution number 1, before you go and compute, say, a correlation coefficient like R, you need to create a scatter plot and just look at it. Is it actually linear? The thing is, you can compute a value of R for any data. That doesn't mean that what you're doing is meaningful. Your correlation needs to be linear, which you just can only inspect visually first. So perhaps maybe in your final project you're going to use linear correlation maybe. Then you would want to inspect your scatter plot before go ahead and computing these things, and then even what we're going to do later in the chapter. Okay. Number 2, if there are outliers, create your scatter plot with a lot of caution. And a good method to follow is find your correlation coefficient by including all the data points, and then find it again by removing that outlier, that suspected outlier, and just see how much influence it really has on this number. Maybe removing that 1 point really jumps this number, either positive or negative, moves it much closer to one of the extremes. Outliers can be very influential on the correlation coefficient. And then number 3, and this is kind of a logic side of it, in everything that we do here in this chapter, correlation does not imply causation. What does that mean? So just because 2 things are correlated, it doesn't mean that one is causing the other one. Now, here's the thing. It's totally natural to think that one is causing the other. In fact, That's really what we're trying to study. I mean, we call x the explanatory variable and y the response variable. The value of x explains the value of y. The value of y is a response to the value of x. Seems like x is causing changes in y. And most of the time, that's exactly true. But we can never say that. We can never make with absolute certainty that x is causing the change in y. All we can say is, hey guys, there's a correlation here. We don't know, we can't say anything more than that, but these as one of these changes, the other one changes, and it definitely seems like they go step in step. And so then I've got this cartoon. You can read that cartoon a little bit later, but the guy on the left feels that there's some causation, and the guy on the right's maybe bringing another perspective in, like that. There's kind of this lurking variable is the idea way back from chapter 1. Okay, moving on. Now we're going to get to the linear regression. The linear regression is we're going to go further than just finding a value of r. Okay, the value of r is really, really helpful, but we want to find what is the equation of that line that would model those data points. Okay, so I say a couple things, right? X is the explanatory variable. We say that again. Y is the response variable. And finally, we get to practice number 3. So let's do that together. I need to grab a new page. You guys have just been staring at the same thing on the page for several minutes. Hopefully you're reading along with the lecture with me. Okay, let me read number 3. Consider again that enrollment and burglary data, same data. We're going to use Statcrunch to determine the linear regression equation. You can do it in just a couple of clicks, and we're going to round our values to 3 decimal places. Okay, so with that same data, now actually, one thing, if you switched all of your enrollments to be in thousands, go and change those back. So it's just 32, 31, 53, and so on. Okay, once they're back to just the 2-digit numbers, then go to Stat, and then Regression, and then click Simple Linear. I'll do that myself as well. Stat, Regression's about halfway down, and then Simple Linear. You're going to need to select, well, that's what I have. You're going to need to select your X variable. We'll pick that to be enrollment. Select the burglaries to be the Y variable, and just go ahead and hit compute. And you'll notice that it's all this data. It's just showing all this data. So some of that we're going to use. Most of it we're going to ignore. Okay. You see there about the 3rd line down, and it'd be nice if I could show you up on the big screen in the classroom and highlight it, but okay, I think you get it. So about the 3rd line down, you should see this. So you might have variable 2 here, variable 1 here if you did not change the names. I did change the names, so I see burglaries equals negative 104.120 plus 5.733 multiplied by the enrollment. And that's it. That's our linear regression equation. So there's the slope right there, 5.733. There's the y-intercept. If you remember the form that we use in stats, y equals ax plus b. You may also find it simpler to just write it in that form with y and x. There's our slope. There's our y-intercept. Okay, and I rounded both of these to 3 decimal places. Statcrunch tends to give very accurate decimal approximations. We don't need it to be that much. A bit cumbersome. Okay, what's going on? So this is the answer to A. Either one of these, I'll go ahead and I kind of like that y and x actually. Let's look at B. If another college exists with an enrollment of 40,000 students, predict how many burglaries would occur each year. Okay, so here really comes the power. Why are we doing this? We want to study the relationship, but we want to make predictions. So now there's this other college. They've got an enrollment of 40,000. And, they would like to know how many burglaries might occur in the next year, and that might help them with their planning, right? So what should we do? We can take the linear regression equation we got from our data, and we'll just see, okay, if there's 40,000 students, what would this equation predict for how many burglaries they would get? Well, the 40,000 students, right, remember, that's the enrollment, that's the X value. The burglaries is the Y. So we can plug in a value for X. And if it's in thousands, then we'll just plug in X equals 40. We'll say, okay, if that college behaves the same way as these other 10 colleges, or about the same way, then we can make a pretty decent prediction. Well, if I plug 40 in, I'm going to get Y equals 125.2. So we are predicting that they would have, we can just say 125 burglaries in the next year. That's if that college, has the same, sort of behavior as our other 10, right? So thing is, we know it's not going to be exactly 125 for this other college. We're just trying to get a good idea, right? The problem continues on the top of the next page, part C. What is the slope of the regression line? And then interpret the slope in terms of enrollment and burglaries. Okay, well, we mentioned a second ago the slope is 5.733. It's always the number in front of X. That's your slope. So there's the slope. Then interpret the slope. Well, we're going to do this exactly the same way we did back in the prereqs in that first video. It's a decimal, so think of it as over 1. And then we can say, okay, the numerator is the change in Y. The denominator is the change in X. So what variables go with which? Well, the Y variable is the burglaries. The X variable is the enrollment. Don't forget that's in thousands. So this actually represents 1,000 enrollment. So what might we say? How might we say it in words, what that slope really means? Here's one way to do it. For every 1,000 students, burglaries increase by 5.733 per year. It doesn't have to be phrased exactly that way, but I think that structure works. For every one, but that's 1,000, the number of burglaries is going to go up by that many. Okay. Oh, I didn't realize I had part D here as well. What does part D say? Say another college was found with an enrollment of 33,000 students, and they had 200 burglaries. Should this data point be considered as an outlier? Okay, so we just got information from this other college. They had an enrollment 33,000, and we can see that they had 200 burglaries. Should we consider that an outlier compared to the data values we already have? Okay, so Statcrunch is going to come in handy again here. I recommend go into Statcrunch in your original 2 columns and put in that new data point, enrollment 33 and 200 burglaries, and go and look at your scatter plot again and see how it changed. And you'll see that when you put that new point in, it's way above the line. Or it's way above the other data points, I should say. Way up there. So my argument is yes, this point is very far from all the other data points. Here's a word that we haven't used yet. We're going to define it in the next video, a residual. Turns out an outlier has a very large, what we call residual. It's very far from the linear regression equation, the line. Which, by the way, I didn't point out where you can actually see the line grafted. It just completely slipped my mind here walking through the video. I should have mentioned it back here in part A. My apologies. When we found this line, you would have noticed in Statcrunch there's a little arrow at the bottom, and so it turns out there's a second page from all this data. So if you click over, you can actually see the scatter plot again, and you can see that line drawn right through them, which is pretty cool. So take a look at the line with the outlier and without. And yeah, that dot, not only is it far from all the other data points, but very far away from the line as well. Okay, that does it for this second video. See you in part 3.